Welcome all to this webinar on MVIs with Kubernetes. It is a high time we talk about this. In the next 1 hour, we can get our heads around the Kubernetes, what value it brings, and how MVIs fits naturally in the cloud solution. My name is Amir Okhri, a cloud enthusiast and working as an architect in Rocket. I'm excited to take you in this journey of MVIs with Kubernetes. For this webinar, I have used following resources. Please feel free to check out as they provide pretty good insights into the world of Kubernetes. The entire source code used during this demo is available at our GitHub repository MVIS Kubernetes. I have used Terminal Emulator, CMDR, but feel free to use any terminal of your choice when you run through the demo samples. In order to make your journey into the world of Kubernetes as comfortable as possible, we have the following agenda. We start with containerization. This will be followed by the orchestrator and the Kubernetes as an orchestrator. And we're going to get our feet wet with a simple example of setting a demo application in Kubernetes. This will be followed how one can easily deploy MVIs into the Kubernetes solution. Please be assured that this webinar is going to be fun. The hype phase of containerization is gone, and we see them as the new industry standard for developing and maintaining applications. Serverless. In serverless management aspect, one does not need to manage the server. We can have serverless platforms which can take care of the infrastructure, and one can just focus on developing the business functions for it. Another benefit of serverless is scale. One can scale the platform depending on the need basis. A serverless function, which can be as simple as image processing, without being aware of how and where it is managed. Pay by use. Pay per invocation of a service rather than maintaining the cost of the entire infrastructure is the added benefit of serverless function. This opens an entire new ecosystem for using public services. A generic hosted application component like authentication service, logging service, analytics can be used under the ambit of serverless functions. Packaging. Self-contained units of functions shields the business function or the application from environmental specifics, easily maintainable through versioning, and makes it much more easier to maintain across various infrastructures. Code reuse. The need to capture the market with a new feature is very important in the current times. The ease of development plays a significant factor into it. And I think containerization brings that into play. One can develop new business functions. Any features can be added quickly or removed without any issues. Automation. The entire infrastructure can be expressed as a code. As a complete unit, one does not need to be more aware of the entire environment and thus brings efficiency in operations. Portability. The complete functions can be moved from one infrastructure to another without having any issues. And the new thing is CI/CD aspect of it. Continuous integration and continuous delivery, where the containerization plays an important part. As a self-contained unit, the quirks of the environmental factors are limited, and hence the stuff which is tested works on all environments. SLAs, one can have guaranteed SLAs within a containerized development. Now, once we understand what are the benefits of containerization and start providing our business functions in the form of container, this opens new challenges for us. And here, the orchestration comes to the rescue. Centralized management. Imagine to be having lots of containers. How does one deal with their versions? How does one deploy software? These are the challenges faced when one has large enterprise business functions in the form of containers. Such aspects of versioning, deployment are being handled by the orchestrator. Increased velocity. The need of the current market is to have rich business use cases being developed quickly and reliably. The orchestration framework provides sufficient building blocks for achieving it. Declarative. The traditional development required not only to specify but also how to achieve a functionality. The market has picked up from the fourth generation language where one specifies what needs to be done and the how part is managed by the 4GL system. The same has been achieved in case of orchestration frameworks where one can specify from CPU, storage and memory in a declarative way and the system manages it. Self-healing. One needed to have a lot of safety nets and processes configured to cater downtime of a business service. One had to provide custom resiliency features, which are not the core part of the business function. These kind of issues are being taken care by the orchestration frameworks, with adequate constructs available to cater in case of failures of a business function. One can focus on the core business functionality. This provides great incentive for giving new features to the market quickly and reliably. Separation of concern. The needs of the customers are varying with respect to SLAs, security, and other cross-cutting functions. A single monolithic product approach to cater all of these aspects becomes a nightmare. From this point of view, having the constructs which allow to be focused at SLA or security gives a much needed edge. And this applies to the orchestrator, which kind of understands these needs and provides them in a declarative way. One can also kind of divide the customers into different categories and provide them non-interrupted services at some premium price. Such kind of capabilities are also provided in the current orchestration framework. The benefits of orchestration. Application building blocks. One of the success factors of every solution is to have small units of focused functions. In other words, the building blocks. This notably provides the flexibility of replacing a specified functionality, but also makes the software much easier to extend and maintain. Orchestration frameworks like Kubernetes are an example of this design philosophy. Specific functionality has been delegated to specific function block. More on this as we go further in the webinar. Scalability. The need of the hour is not only to provide rich features, but also to have the ability for them to scale depending on the load. These aspects of scalability cannot be an afterthought, but should be the main guiding principle of the new cloud-based solution. Cloud native. A software which has been born from the cloud perspective fits seamlessly into the equation of providing cloud-based services. One does not have steep curve in understanding these constructs and can come to the speed quickly. Web-based administration. One can monitor the existing solution for any errors through web browser. There are tools developed for providing monitoring and SLA alerts, thus simplifying the operations aspect of the solution. Here is a glimpse of how a typical MVI solution in Kubernetes world will be deployed. Don't get scared. We will cover all the components, their purpose, and how they provide us the benefits of giving our end customers a feature-rich, scalable, and reliable solution. Welcome to the world of Kubernetes. As highlighted in the previous section, for any successful solution, one needs a solid foundation We call them pillars of Kubernetes. The first pillar is the compute pillar. The ability to specify the computation requirements to the framework in the form of CPU and memory allows us to use our resources more efficiently. The possibility to have granular configuration to specify the computational requirements at each business function is very useful and gives us much more control over the computational resources. To provide thresholds for our computational requirements and the possibility to instruct what needs to be done in case thresholds are crossed makes us capable of meeting the SLAs of our application. Networking. Networking plays an important role in case of distributed solution. The expectation that the intercommunication works reliably is very important. This would require a lot of involvement from the infrastructure and operations. Kubernetes takes over this part by providing constructs like over network, endpoints, services, and ingress. This makes management of networking much easier. It provides us the right abstraction for specifying the rules of our business case and at the same time gives us the tremendous flexibility in changing them as per our needs. Storage. Any production-based system requires storage for storing its state. The traditional development of providing disk, volume, and network storage are still viable. We also have now use case specific storage like object storage. And last not but least, we have various storage types being provided by cloud providers. Kubernetes provides the flexibility of allowing us to specify which storage provider we want to use for our solution. Apart from specifying which storage, one can also have the flexibility of specifying how much storage capacity we need in forms of claims. More on this as you go further. The storage provided to our business functions are durable and maintain the integrity of our data. Let's go more in detail into compute constructs. Pod. A pod represents a business function and is atomic unit in the whole solution. A pod can contain multiple containers which are required to fulfill the business function. The recommended way is to have a single container, but if the possibility of consolidating the business function in one container is not possible, namely when we are migrating the legacy application into Kubernetes world, one can have multiple containers within one pod. Every pod has its own IP address within the Kubernetes cluster. Pods are mortal and when they die, they are recreated with a new IP address. Containers within a pod can communicate with each other without the need of an IP address. Replica set. In order to support the scaling or descaling of a business function, we have replica sets. They provide us the capability of having multiple pods and in case of failures, the ability to recreate them automatically. Deployment. The deployment provides us the capability of maintaining our business solution. They provide us the constructs of versioning and thus one can upgrade our solution from one version to another. The upgrades can be staggered in a way that there is a minimum impact on the existing systems. This provides the tremendous flexibility of rolling a new version of our business service without having downtime and thus saving a huge amount of time in getting new features into the market. Normally, for a business case to be served, it requires a bunch of intercommunication between various business functions. Let's term the business function as pod. Their job is to provide smaller, granular functionalities. So, in order to have the business case served, one needs to communicate across the functions. For communication, one needs a particular IP address and obviously routing mechanism. One can resolve this by adding this IP address of individual pods in some kind of a routing table in our networking infrastructure. This would require a lot of configuration.
What if the pod dies and gets a new IP address? We need to again change entry in the routing table. There is another concept of networking called overlay, which is kind of logical and runs over our physical networking solution. What if this could be provided out of box? And this is precisely what done by Kubernetes. So pods can communicate with each other without much reconfiguration, and again, this can be achieved through a declarative way. For this declarative way of defining networking requirements, Kubernetes has provided various constructs, namely endpoints, services, and ingress. Kubernetes pods are mortal. They are born, and when they die, they are not resurrected. If you use a deployment to run your app, it can create and destroy pod dynamically. Each pod gets its own IP address. However, in a deployment, the set of pods running in one moment in time could be different from the set of pods running that application. This leads to a problem. If some set of pods, let's call them backends, provide functionality to other pods, let's call them frontends, inside your cluster, how do frontends find out and keep track of which IP address to connect to so that the frontend can use the backend part of the workload? Inter-services. In Kubernetes, a service is an abstraction which defines a logical set of pods and a policy by which to access them. Ingress. In Kubernetes, an ingress is an object that allows access to your Kubernetes service from outside the Kubernetes cluster. You configure access by creating a collection of rules that define which inbound connections reach which services. In order to understand the full power of ingress, one needs to understand what other options are provided, namely node port and load balancer. Node port. Kubernetes will allocate a specific port on each node to that service, and any request to your cluster on that port gets forwarded to the service. This is cool and easy. It's just not super robust. You don't know which port your service is going to get allocated, and that port might also get reallocated again at some point. Load balancer. Here, one needs to be having some external load balancer functionality in the cluster, and this is typically implemented by a cloud provider. Every time you want to expose a service to outside world, you have to create a new load balancer and get an IP address. Ingress. Ingress on the other hand is completely independent resource to your service. You declare, create, and destroy it separately to your services. This makes it decoupled and isolated from the services you want to expose. It also helps you to consolidate routing rules into one place. A Kubernetes ingress is a robust way to expose your services outside the cluster. It lets you consolidate your routing rules to a single resource and gives you powerful options for configuring these rules. Endpoint. This holds a logical connection from the service object to the pod. So in case the IP address of the pod changes, only this endpoint object inside the service needs to change. The storage constructs. Persistent volume. The persistent volume is an administrative object for defining persistent storage in Kubernetes. Persistent volume provides a pointer to the actual physical storage that is connected via the container storage interface. This object is provisioned by the administrator and persists beyond the lifetime of a pod. Persistent volume claim. When an application makes a request for storage, it is made as a persistent volume claim, which makes a storage volume usable in a pod. Persistent volumes can be provisioned manually or dynamically via a policy. Storage class. The storage class object is a collection of persistent volumes with the same characteristic enabling an application to pull the right type of storage that needed for a given development. Here are some of the other MVU courses which I would highly recommend to check out. MVIs with Kubernetes, Containerization and Orchestration. In this, we will understand what is the need of orchestration and benefits of it. MVIs with Kubernetes, setting up and deploying sample app. In this, we will be experiencing how to deploy a sample app into the Kubernetes. MVIs with Kubernetes, setting up MVIs with Redis Server. Here, one will deploy MVIs in Kubernetes along with Redis and in-memory data store. MVIs and containers. How easy it is to run MVIs as a Docker container. And finally, MVIs in prominent cloud providers like Amazon, AWS, and Microsoft Azure.